Hello, let's look at the following question. When a prime can be written as a sum of two squares. Let's start with small primes, with experiments. The first is 2, and it is obviously a sum of two squares. 2, however, is a special among primes. It's only even prime, so let's separate it from the rest of our story and look at all other primes. Starting with 3, and 3 it is not a sum of two squares, because we have to use as at least one of the summands, we have to use a square of something larger than 1, and 2 is the next after 1 squared is larger than what we have, so impossible to write as a sum of two squares. 5, however, is 2 squared plus 1 squared. 7, which is the next after 5, again is impossible to write, because we have to use larger, at least larger summands, so it could be 2 squared and 2 squared, which is actually 8 is already larger, or 3 and 1, which is also larger than 7, so it is impossible. And so is 11. 2 and 2 is smaller, 3 and 1 is smaller, and the next 3 and 2 is larger. It's actually the answer for 13. 3 squared plus 2 squared gives 13. After 13 comes 17, and again it is a sum of two squares, 4 squared and 1 squared. After 17 is 19, and it is not by the very similar method. And 23, which comes after 19, again is not possible to write as a sum of two squares. So let's stop here and try to see any pattern in the answers. The pattern comes, well, it's really a trick now, because I'll have to direct into the right path. So the right way of looking at this is to look at the remainder of our prime when we divide by 4. So when we look at those remainders for all the primes we examined, for 3 the remainder is 3, for 5 it is 1, for 7 it is 3 again, for 11 it is 3, for 13 it is 1, and so is 17 has remainder 1. 19 has remainder 3, and 23 has remainder 3. And now the pattern is clear. Each time we have remainder 1 we have a solution, for remainder 3 case we don't. So here is a conjecture that a knot prime P can be written as a sum of two squares. It happens if and only if the prime is congruent to 1 mod 4. So I'm using this modular arithmetic notation. So this is the main conjecture. We can, that's supposed to be a criterion for a prime to be a sum of two squares, and that means it works both ways. So we could prove one way, which is easy, say from knowing that we have a solution to knowing that P has to have remainder 1. That is just an example of simple arithmetic modulo 4. So let's look what we have. Well, we have a knot prime, and we have it written as a sum of two squares, so one of the summands has to be odd. Let's assume it to be the first one, so let's just fix A to be odd, or rather A squared, and B squared will have to be even. But if B squared is even, then B is even, and so B squared is actually divisible by 4, so that is 0 mod 4. And after eliminating it, we can say that P is congruent to a square mod 4. What remains now is to look at what are possible odd squares mod 4. So there will be squares of odd numbers, and odd numbers have either remainder 1 or remainder 3 mod 4. And modular arithmetic says it doesn't matter what the number is, as long as you know its remainder, you know what the remainder, the square will have. You just need to compute the squares of these numbers and, if necessary, take the remainder. For 1, the square is 1 and it is its remainder. For 3, the square is 9 and the remainder is still 1. So we have a conclusion that any square, any odd square, is congruent to 1 mod 4. And putting these two together, we have our desired implication. From knowing that P is the sum of two squares, we can be sure that P is congruent to 1 mod 4. So the last remark is about the number of solutions if we have them. So suppose that we have a solution, and obviously we can flip the sign of say A here and B here, and change the roles of A and B. So we have here we have in general 8 solutions. If we have 1, we have 7 more, unless some of them coincide. So is it all? The answer is yes, and the justification comes from the fundamental theorem of arithmetic in Gaussian integers. So let's look at the factorization which corresponds to this. Factorization Gaussian integers for this odd prime P. It can be written as A plus IB, with those A and B times the conjugate A minus IB. So that is a factorization into primes in Gaussian integers. We already saw that these are irreducible, and so it is unique. We have to be careful. It is unique up to invertible factors, plus or minus 1 in front of any of the factors and then compensated for the other, or plus or minus I. But if we look at what these invertible multiplications by those invertibles do to our solutions A and B, they will be exactly these 4 or rather 8 possibilities. So solution is unique in the same way. Up to changing the signs and swapping perhaps the roles of A and B. So that is just the consequence of the unique factorization in Gaussian integers. See you later.